Hello, we are glad to present our paper, Top-Down Beats Bottom-Up in 3D Instance Segmentation. The research has been done by Maksim Kolodiazhnyi, Anna Vorontsova, Anton Konushin, and Danila Rukhovich. 3D point cloud segmentation is the task of grouping points into meaningful segments. In case of 3D instance segmentation, such a segment consists of all points belonging to a single object. Two major 3D instance segmentation paradigms have been introduced so far. Bottom-up methods learn per point embeddings and use them to cluster points so that they form a set of proposals. Top-down approaches directly predict instance proposals as object proxies, which are then filtered via non-maximum suppression and refined via mask segmentation. Top-down methods have several advantages over bottom-up ones. They do not require domain-specific clustering algorithms and are faster on inference. But these benefits are gained at a cost of prediction quality. However, we prove it possible to create a simple top-down approach that beats current state-of-the-art in both inference speed and accuracy. Our main contributions are as follows. We propose the first fully sparse convolutional cluster-free 3D instance segmentation approach, named TD3D. Then, we empirically prove that TD3D is the first top-down method that supersedes bottom-up competitors. Finally, we perform extensive evaluation on both indoor and outdoor benchmarks, and establish a new state-of-the-art in accuracy and speed of 3D instance segmentation. Here, we compare TD3D with conventional grouping-based approaches. TD3D runs in two stages. First, it detects 3D objects in a point cloud and extracts the corresponding 3D bounding boxes. These bounding boxes are interpreted as initial object proposals and then refined with a lightweight network to obtain final instance masks. All operations in the pipeline are implemented with 3D sparse convolutions. The key novelty is the first step, where a time-consuming grouping operation is replaced with a simple 3D detection head. Our proposal generation is based on an FCF3D, a 3D object detection method that is proven to be efficient for indoor scenes. First, a point cloud is processed with a sparse 3D ResNet followed by an FPN. Then, the outputs of three FPN feature levels are passed through a shared detection head which outputs 3D bounding boxes. After filtering, these boxes serve as initial proposals. The points in each bounding box are extracted by an arrow-eye extractor. Finally, a refinement head, which is a sparse 3D UNet, transforms initial proposals into segmentation masks. We train our model end-to-end with both 3D detection and 3D instance segmentation losses. The detection loss is a sum of a focal loss for classification and an area loss for bounding box regression. The segmentation loss is a binary cross-entropy loss. Let us look at 3D instance segmentation results obtained in three benchmarks. ScanNet and S3Ds both contain indoor scenes, while STPLS3D is a large-scale synthetic outdoor dataset. To compare with other 3D instance segmentation methods quantitatively, we measure a mean average precision score. On ScanNet, TD3D outperforms top-down competitors by a large margin, and also it ranks the first in the hidden test leaderboard. In the meantime, our method is much faster than existing approaches, processing as much as 7 scenes per second. Apart from ScanNet, TD3D achieves state-of-the-art accuracy on the indoor S3Ds and ScanNet 200 datasets, as well as on the outdoor STPLS3D dataset. Regarding inference speed, we should note that all operations of TD3D are executed on GPU. In contrast, existing methods with comparable accuracy perform grouping operations on CPU, which makes them significantly slower. To conclude, the state-of-the-art inference speed and 3D instant segmentation accuracy can be achieved with a simple top-down method, purely executed on a GPU. Feel free to visit our GitHub, where you can find the code and pre-trained models. Thanks for your attention.